Hello and welcome back to the part 2 of the activity. Now in this part we will continue solving the activity we did in the previous video, and then this time around we'll try solving the NewtonRaphson portion. So we'll try writing a code for our NewtonRaphson algorithm to solve this nonlinear equation. And then, just like the previous video where we did the bisection, after the activity you are expected to repeat the same process to solve this particular function. So let's go to our canvas and then prepare for the NewtonRaphson. So the Newton's method. Now for the Newton's method first deals with, so given any nonlinear function, say f of x, right? Now the Newton's method would need the derivative f prime of x, right? So it means it's going to make use of f of x and then f prime of x, and then it says that for you first assume an initial value x naught, and then your new approximate root, let's say x1, will be given as what? The formal value x naught, right, minus what? The functional value of x, f of x, what? X naught divided by what? F prime of what? X naught. Sorry. So this becomes the new root, and then you perform this iteration several times until you get your number of iterations, or you meet a particular tolerance, right? So from here you would have to compute f of x1, right, and then check whether the value of this, the absolute value of this, is less than a given tolerance. So if the absolute value of this is less than a given tolerance, then we can now decide to terminate our loop. So here we would still use a while loop, right, and then check those conditions. So let's jump to our terminal and see what we can do from here. So we are in the terminal. We first create our C file. This time we'll call it newton.c, and then we include our standard input output. So we include our standard inputs library, and then this time around we would still use the absolute value, so we would still include the math library, right? So the math.h, and then we want to define our function. So we define our function f of x, and then the function will be the macro. So we have the x star x minus x minus 1, and then we define what? We define the derivative. So I'll call this diff. Bear in mind the macros must be in caps. So diff of x, and then this time if you differentiate x cubed minus x minus 1, you get 3 star x, so that will be 3x squared, right? So that will be star x here minus what? Minus 1, because if you differentiate this x you get minus 1. So we are done defining our macros. So we give our function prototype. As I said, this will also return a float, and we'll call this Newton. So let's call it NewtonRaphson. and then Newton, let's keep that well, and then the NewtonRaphson. Now here it will receive a float argument, but then we first assume an approximate root, so that will be x, so we will call this x naught, right? So x naught, and it receives another argument, tolerance, so that will be tau, right? Now from here we also say that we also now include our int main function, right? And then this will return void, so we give it a void, and then we try to, so here to we call, let's say we define a float called answer, right? And then we print f answer. So first we define our answer to be equal to what? Our answer is equal to the so answer is equal to NewtonRaphson, and then here becomes, and then we will supply it with an initial guess. So here we can give it 1, and then the tolerance can be 0.000001. okay, so and then we do what? Float. So the root is what? The root is %f, right? Then we go to a new line, and then we try to provide it with the answer variable, and then we end this line as well. So now we can now go below our function, right? And then do what? Try to declare our float, our NewtonRaphson function here. So NewtonRaphson, we give it the same name as we did in the prototype, which takes in an input argument x naught, and then float tolerance, right? And then this time around we do what? We make sure that, so now we need a stopping criteria, so we'll declare a float. This should be an integer, so int called stop, right? And then we have, so stop should be equal to probably 0, and then we would need a new x value, that will be our x1, or yeah, so our new x, so we can call this x, but this should also be a float, so float x is equal to what? Okay, let's not give it any value, so float x. So now we can start our loop by saying while, right, our stop is equal to 0, then we should try, so while our stop is equal to 0, what should we do? We should first assign our new x, right, to be equal to the old x, that's x naught, right, minus what? X naught minus, now so here this is going to be the functional value f of x naught, right, divided by, so divided by the derivative, right? So the derivative, so that will be diff of what? X naught, right? And then we terminate this line, and then from here we decide that now we check if what? If the absolute value, so f abs, that's from the math library, so the absolute value of f at x, f of x is what? Less than, if the absolute value of f of x, right, is less than what? Is less than the tolerance, right, then we should perform a specific task, and this task should be, we should let r to be equal to our root. So our root should be equal to x, and then break out of the loop. So let's try breaking, but then let's define our root here as well. So our root will also be a float, so comma root here. So now we have this two defined, and then what now? Else if what? So if this is true, then it should return this and break out of the loop, right? And then let's try returning the what? The roots. So let's save this and see what happens. Sorry, the return shouldn't be inside the while loop, but then outside it. So that will be return the roots. So we have that, and then let's save it and see. Sorry, so let's save this and then try compiling it and see. So GCC interval, that will be Newton, right? Newton dot C, we want the output to be Newton dot X, right? So Newton dot X, then we have an error. It says that yes, this should be comma, sorry, not semicolon. So here we give it a comma. Yes, so let's resave this and see what happens. Here we recompile, and then we see they said reference to NewtonRaphson, return exit status. So in function main, undefined reference to NewtonRaphson. Let's see what happens here. Undefined Newton, sorry, so we did not, we have to make sure that the spelling here is correct. So that's Newton, and then yes, this is the same as the one we have here. So let's save it and see. Okay, so we don't have any error again. So now let's run our code and see. So // Newton dot X. Yes, so the code doesn't terminate, or the loop doesn't terminate. So we do Control C to close it, and then let's go back and check what the problem is here. So the reason why the loop stopped, it refused to terminate, was that here we said if this is this, right, we should assign the root to be equal to X, right, and then we should break, right? But then what if it is not? Okay, what if the functional value is not less than the tolerance? What should happen? We didn't say anything, so it will continue to verify until this is less than the tolerance. Do you get? So right now what we would have to do is to add an else, right? What it should do. So else what? Then we now, after assigning x naught, after computing this, right, we have to reassign the x value. If it is not less than the tolerance, then we have to reassign the x value to the tolerance, right? So this will be else what? Our x naught, right, is equal to x, right? And then we end that line as well. Now when we save this, right, and then we recompile this, so sorry, GCC, right, Newton dot C dash O Newton dot X, right, dot X. Once we recompile this, we don't get any error. Let's run this Newton dot X, and then now we are told that the root is what? 1.3244718. So basically now the program runs well. So it means that we would have to choose our initial root, that's the x naught, wisely, right? So here we chose it to be 1, so it did that. So you can actually add more features to this. You can add a counter that would be counting to tell you the number of times it's run, but then you would have to do something to it. Make sure you tweak it well, and then try doing this and then changing the function to solve the second equation in the activity, right? So try and see if you can use it to solve the second equation. So x cubed plus 2x squared plus x minus 1. For now, this will be the end of this second version of the activity. The next one would be using it to create a second method. You can try that on your own or watch the next video to see how we do it. Thank you.